So we've talked about the 5-number summary, the minimum, Q1, median, Q3, and the maximum. Notice those are in order of smallest to largest. We're going to use those numbers, the 5-number summary, to help us build box plots or box and whisker plots, if that's what you like to call them. So the first blank there, the 5-number summary, divides the distribution roughly into quarters, like 25% between each number. This leads to a new way to display quantitative data, not a histogram, not a dot plot, not a stem plot. We're talking about box plots today. How do you make a box plot? Well, we need a central box. It's drawn from the first quartile to the third quartile. We draw a box with those as our endpoints. We'll put a line in the box that marks the median. So the median will be somewhere between Q1 and Q3. And the lines that extend out to the right and to the left, those are called whiskers sometimes. They'll extend out to the furthest points that are not outliers. So it'll reach out up high to the biggest point that's not a high outlier, and it'll reach out down low to the lowest point that's not a low outlier. If we do run into outliers, we'll put an asterisk for each one of those. So my very crude representation of a box plot, you go from Q1 to Q3, there's the box, the median, you put a line somewhere between those two, wherever the median falls. Doesn't have to be exactly between the two. Have a whisker that extends out to the lowest number that's not an outlier. Have a whisker that extends out to the highest number that's not an outlier. And then if you have any outliers, you put an asterisk for each one. So that's my very crude, rudimentary drawing of a box and whisker plot. My drawings are going to get better though, I promise. Let's take a look at example 3. Example 3 says compare the distributions of the McDonald's data, the beef sandwiches versus the fish sandwiches, using box plots. So what would be most helpful to start with is the 5-number summary for each set of data. I'm going to go ahead and make my x-axis here. I think 0 to 50 should cover it. In fact, I think the highest value we saw was 43 grams of fat. So I'm just going to go from 0 to 50 and count by 5s. And then the 5-number summary for McDonald's beef sandwiches. Let's go ahead and bring that back. We've got 9 for the minimum, 21 for Q3, 26 for the median, 29 for Q3, and 43 for the max. Now the question is, were there any outliers? And you may have already guessed that one of the sandwiches in the McDonald's data is indeed an outlier, but we now have a way to prove it or show it mathematically with our IQR rule, right? So I want to look at maybe a potential high outlier here in the McDonald's data. And to do that, we need to know what the upper fence would be. So for the beef data, the upper fence, we would do Q3, which is 29, Q3 plus 1.5 times the IQR. That will build our upper fence, and any data beyond the edge of that fence would be considered a high outlier. So 29 is Q3 plus 1.5 times the IQR. The IQR is simply just Q3 minus Q1. Gives us an upper fence of 41, and we do indeed have a data point beyond that upper fence, which is 43. Thus, 43 would be considered an outlier for the McDonald's data. So when we make our box plot, we'll have to put an asterisk at 43. And then I believe the highest value that was not an outlier, the otherwise highest value in terms of the fat per gram, so the beef sandwich was 31. And we can go back and look at that, but I think the highest value that was not an outlier would be 31. So that's for the beef. For the fish data, we'll get the 5-number summary here again. For the fish data, the minimum, Q1, the median, Q3, and the max. It turns out there are no outliers in the fish data, but now if this were a test question, for example, you'd be expected to show that, right? So I'll leave that to you to show that there's no high outliers in the fish and there's no low outliers in the fish with the 1.5 times IQR rule. And furthermore, you should also be able to show that there are no low outliers in the beef data with the same rule. So far, I've shown that there are indeed there is indeed at least one high outlier. There is exactly one high outlier in the beef data. I'll leave the others for you to show. But for now, there's no outliers in the fish data. So we can go ahead and start making our box plots. We're going to use the same axis for both. So starting with the beef, I know I have a minimum of 9, so my lower whisker is going to reach down to 9. And then for my box, I know the box goes from 21, that's Q1, and then I'll put a marker at the median, which is 26, and then a marker at 29. So this is going to make my box from Q1 to Q3 here. And then 31 was the highest sandwich that wasn't an outlier, so my upper whisker will reach to 31. And of course, I've got an outlier at 43. So there's my box. My whisker will extend down to the left to 9, the minimum. And then up to 31, that's the highest value that wasn't an outlier. And then of course, I've got my outlier at 43, so that gets an asterisk. Lovely. I told you my box plots would get better. Some nice straight lines here. So that's how we use the 5-number summary. There's the minimum value, Q1 to Q3, those are the edges of the box. The median gets a line and wherever it falls between Q1 and Q3 in the box. Upper whisker, in this case, goes to 31 because that was the biggest value that wasn't an outlier. And then we have an asterisk here at 43 to represent our high outlier in the beef data. Okay, what about for the fish? The fish starts at 9 as well. I'll use a different color here for the fish data. We can put a mark at 15 for Q1, a mark at 19 for the median, 24.5 is Q3. That's going to outline our box from Q1 to Q3. And we'll have whiskers going down to 9 and up to 33. There are no asterisks here since there are no outliers in the fish data. And these are what's called parallel box plots. They are floating above the same x-axis, therefore we can compare the numbers in a similar fashion. So they're on the same x-axis, they're floating above it. This is what's called parallel box plots. It's a great way to compare multiple distributions. So now we've constructed our box plots. We've got the fish on top, and I really should put a label here, right? Like fish, beef. So I've got x-axis. I know this is the fat in grams for each sandwich. And then I'm color coding here. Red is beef, of course. And then the blue color here, that's for fish. So now we've got our graphical displays. Let's go ahead and make our comparison here, right? Let's talk about the SOX, shape, outlier, center, spread. So we can say the fish graph, probably symmetric would be the best answer here, right? This is roughly symmetric. But looking at the beef, I see the median here and then a long stretch down this whisker. Remember, the median is the 50th percentile, so 50% of the data stretches down this way. And then 25% of the data from the median to Q3 is all packed into that area right there. And then, of course, we have our high outlier here. Probably left skewed would be the best answer for beef. I know it does have one high outlier. So I would say roughly symmetric for the fish, right? The fish graph appears to be roughly symmetric. In the beef graph, we would say skewed to the left probably, and that might be more apparent from a dot plot as well. But we have 50% of the data stretching this way, and then the other 25% of the data is here, and then the other 25% of the data above Q3, but we know that just one data point is up here at the high outlier. So that's the shape. And then in terms of SOX, we can go to outliers. We know we've got one high outlier in the beef. That's very apparent now. So there's one high outlier in the beef data at 43 grams of fat. However, there are no outliers in the fish data. And in terms of the center, those are pretty easy to compare now. We know exactly where the medians are. Clearly, the center for fish is lower than for beef. So fish sandwiches tended to have lower fat, right? We can look at the median right there. So we know beef has a higher center at 26 grams for the median than fish. Their center was only at 19 grams. So we've talked about shape, outliers, center. Last but not least, the spread. Thanks to this high outlier, the beef graph has more variability, right? So in this case, beef is more variable. It goes from 9 grams to 43 grams than the fish data, which only goes from 9 grams to 33 grams. All right, beautiful. We've constructed parallel box plots, made our comparison with socks. Let's go ahead and move on. So we've got some questions to answer here related to quantitative data. Question 1, what is a resistant measure? Is the mean a resistant measure of center? So a resistant measure means that it's not influenced by extreme values or skew, right? It's not like pulled by outliers or right skewed or left skewed. The mean is definitely not a resistant measure. Right? When we have to calculate the mean, we have to account for those larger values or values that make it skewed. So the mean is not resistant. In question 2 there, how can you estimate the mean of a histogram or dot plot? So not calculate, we know how to calculate the mean, right? Add up all the values, divide by how many there are. How can you just simply estimate it by looking at the histogram or the dot plot? Now this one takes a lot of imagination. You have to picture the histogram or the dot plot being made out of like solid material, and it's the point where it would balance, the graph would balance on your finger. Right, so again, a big imagination, that's your estimation for mean. Looking at a histogram or a dot plot would be the balance point of the graph if it were made out of solid material. Question 3, is the median a resistant measure of center? Yes, indeed it is. The median is a resistant measure of center. It's simply just the midpoint, the middle of the road. It's not subject to those extreme values. It only measures location. What value is located in the middle of the distribution. It doesn't have to account for those larger values in the same way that the mean does. So yes, the median is resistant. Q4 says, how does the shape of a distribution affect the relationship between mean and median? Well, if a graph is roughly symmetric, that means it's pretty well balanced. The mean and median are going to be about the same. However, if you start to get skew, for example, if it's right skewed, the mean gets pulled up towards the larger values, right? It has to account for those larger values, so the mean will be greater than the median in a graph that's right skewed. And similarly, in a graph that's left skewed, the mean gets pulled down, so the median will be the larger of the two. So right skewed graph, the mean is bigger than the median. A left skewed graph, the mean is actually smaller than the median. And that is because the mean is not resistant to that skew. It gets pulled in the direction of that skew, whereas the median stays relatively the same. It's resistant to the skew. Okay, Q5 says, what is the range? Is it a resistant measure of spread? Explain. The range, of course, is just the difference between the maximum and the minimum, right? You do the max minus the min to get the range. It is definitely not a resistant measure of spread because it has to account for the very largest value and the very smallest value. So it is not resistant because it deals with the most extreme values. Question 6 there, what are quartiles and how do you find them? Quartiles like Q1 or Q3, right? Each quartile goes up another 25%. I guess you could call the median Q2. How do you find them? So my clue or my hint for that is start with the median. So start with the median, the very middle point of the data, and then to find Q1, just chop the lower half of the data in half. So it's like finding the median of the lower half of the data. And then to find Q3, the third quartile, the 75th percentile, look at the upper half of the data and chop that in half. So, like finding the median of the upper half of the data. So, in general, start by finding the median of the data set, then go to the lower half, find the middle of that, and go to the upper half, find the middle of that, and you'll have Q1 and Q3. Question 7. What is the interquartile range, otherwise known as the IQR? And is the IQR a resistant measure of spread? We know it's just the difference, Q3 minus Q1, and IQR is indeed resistant in the same way that the median is resistant. It's a measure of location. the 75th percentile minus the 25th percentile. IQR is a resistant measure of spread in the same way that the median is resistant. Question 8, it's not on my page here, but I'll leave that one to you. What is the 5-number summary? How is it calculated? We've already discussed that. You know what the 5-number summary is. That's what we started this video with. And we will end the video right here. So that's all for these notes. I'll see you in class.